Hi. Okay, so good morning. And so today we're going to talk, we're just going to really kind of do the introductory topics of thermochemistry. And then we'll, next week we'll get more into the nitty-gritty details of the transfer of energy, primarily through heat and work. So, as I said yesterday in the previous lecture, that in chemistry, we are often concerned, and actually in all the sciences really, we're concerned not just with matter, but we're also concerned with energy. And the reason for that is pretty practical, which is that energy has a huge impact on our lives. We require the transfer of energy through food in order to survive. We require the transfer of energy from the atmosphere in order to stay warm, or even to stay cool. We require the energy of the sun to heat up the atmosphere. So energy is very important for the running of our society. And, just like one kind of little tidbit I was reading the other day was that, if there happened to be a solar flare that the direction of it were in the path of the Earth's orbit, it would probably wipe out quite a bit of the electrical grid in the world. And so we would be without energy for a while until it got repaired. So we are very dependent on energy. And we, as it gets colder in the winter, of course, we know that, we realize that. Now, so what we're going to do is we're going to start with some very basic information. It's essentially middle school physics, and that has to do with the idea of kinetic and potential energies. Okay, so I'm going to bring up the diagram of this problem. Oops. There we go. So this is the first ALEKS problem involving energy. And it says you're going to use the conservation of energy, the law of conservation of energy, to predict the qualitative exchange. So qualitative just meaning we're not worrying about numbers per se. We're just looking about big or small or that kind of thing, greater than, less than. The qualitative exchange of kinetic and potential energies. So it is useful to think of energy as something that can transform. And we're going to be a little bit loose about what energy is. The general definition that we would use in a course like this is that energy is the potential to do work, the capacity to do what's called work. And we'll talk about work, probably not today, but maybe today, we may get to it. The potential to do work, okay? And so the idea then would be that energy is not created nor is it destroyed, it's transformed. So energy goes from one form to another. So one concept idea of this would be that energy transforms between two types of energy. And one is called kinetic energy, which is the energy of motion. And that's useful for us in chemistry because we picture atoms and molecules as being these little particles that are moving around, right? In a solid, they're vibrating back and forth like springs. In gases and liquids, they're moving around, bouncing around. So they have kinetic energy. But there's also this concept of energy called potential energy because we don't observe it occurring. Like we see kinetic energy when you see a bus driving down the street, you can see that motion. We can see motion very well. So we see that there's energy in some sense. But potential energy, we don't see it because it's in the material, but it's not actually actively doing anything, or at least it appears as though it's not actively doing anything. So we have potential energy. And what will happen is potential energy can be transformed into kinetic energy and vice versa. So in a sense, when we charge up a battery has potential energy if it's not being used. But when it is getting used, it will heat up the environment, right? The air around it gets hot. The metal casing of a cell phone gets hot as you use it. It's being transformed into kinetic energy. So here's an example. This is gravitational potential energy and then just really basic kinetic energy, right? So the idea is that as you ride up a hill, you slow down. And as you ride down a hill, you speed up. And kinetic energy is the energy of motion. So the faster you're going, the more kinetic energy you will have. The higher up, so potential energy is really energy based on position. Okay, so we'll see a little bit later in the course that the position of an electron relative to the nucleus is a form of potential energy. So the higher up something is, the more gravitational potential energy it has, right? So we don't really worry about gravity all that much in chemistry, except, for, dropping things on the floor. But in terms of chemical reactions, we don't really worry about gravitational. But this is just an analogy to talk about the idea of potential. So the higher up in a mountain is that you are, the more potential energy you have, right? So if you've ever ridden a bike up and down hills, you realize, oh yeah, if you go up to the top of the hill, now you can coast down real fast, right? Yeah, potential energy is being converted into kinetic energy, okay? So we have some questions here. Where would the bicyclist have the highest potential energy? Well, that would just be up at the highest point along this path. You're furthest away from the center of the earth. That's where you'll have the most potential energy. So it looks like it's F, right? The highest up you could be would be F. Where would the lowest potential energy be? So where would the bicyclist have the lowest? Well, that'd be the closest to the center of the earth. And so that would be down at D. Right, D would be the
Why
lowest.
wouldn't it be C, where he would have the highest potential energy? I mean, that's right before he goes downhill,
Because F is higher than C.
but it's heading uphill.
Doesn't matter the direction, it's just your position. All matters is what your position is.
Okay.
Where would the bicyclist have the highest kinetic energy? Now you have to think about this. Imagine it's moving. Imagine the bicycle is actually moving. So it's going to go from A, it's going to go downhill and then up to B and C. It may very well be that the bicyclist has to do some pedaling between B and C, right? Because B and A are about the same position. So they probably have to pedal a bit to get up to C. And then you start increasing your speed, right? Just like you drop something. If you drop something, it starts off very, very slow. It's not moving at all. And then it goes faster, faster, and faster. So the highest kinetic energy is usually at the minimum, at the lowest point along the curve. So the highest kinetic energy looks like it's a D. It's a position D. That's where you'd be going the fastest. Okay. Now, what about the highest speed? Well, speed and kinetic energy are related to each other. The faster an object moves, the more kinetic energy it has. So where you have the greatest kinetic energy, you're likely to have the greatest speed as well. So the answer for that one would be the same as the previous one. You would be at position D would be the greatest amount of speed. That's where you're moving the fastest, okay? The argument behind lowering speed limits of automobiles, I mean, I guess there's a couple arguments you could make, but the simplest one is kinetic energy. The slower an automobile moves, the less kinetic energy it has. So if it hits something, whether that be a pedestrian or a bicyclist or a person on a scooter, or even another car, right? The slower that object is moving, the less kinetic energy it has. So the less energy it has to transfer over to the object that gets struck. So I haven't seen these ads lately, but they used to have these ads that said the fatality rate of a pedestrian being hit by an automobile at 40 miles an hour was 80%. At 30 miles an hour, it was 20%. So it's a very dramatic shift there, right? And that has to do with kinetic energy. The less kinetic energy the object has, the less energy it has to transfer over to the object being struck. Okay. Would the bicyclist's kinetic energy be higher at F or D? Well, the F is higher. So we'll think about this practically, right? Like if you roll down the hill, you're going to go real fast, right? So you're really going the fastest at the minimum. That's where you're going the fastest, where you have the least amount of potential energy, but you have the most kinetic energy there. And then as you go up, you start slowing down, right? You're slow, slow, slow. Probably this bicyclist wouldn't be able to get up to F without pedaling, right? Because F is higher than C. So as you go down the hill, you're going to start off slow, go fast, slow down, slow down. You're probably not even going to make it up to there without pedaling. So the F would have less kinetic energy than D would have. More potential, but less kinetic, right? Now, obviously, some energy is going to be lost to the environment, right? Like as this bicycle is riding up and down these hills, some of the energy is transformed into heat, friction on the road. So there's some loss there, but still the general qualitative trend is the same. There's a lot of questions with this one, right? So let's look at the next one. Would the bicyclist's potential energy be higher at F or D? Well, F is higher, so it has more potential energy than D does, so higher potential. So F, again, has the highest amount of potential energy. Total energy, okay? So at F or D, from a simple perspective, without getting more complicated, we're using conservation of energy. So the idea is that along this path, the bicyclist has the same amount of total energy the entire time. And this was a debate in the 20th century by astrophysicists. The idea of how much energy is in the universe and does it change? Do we have more or less energy in the universe as time goes on? And so the two competing schools of thought, one was that actually there's probably energy being formed at all times. And if we have good enough telescopes, we'll be able to see, the creation of new energy coming into the universe through these, well, there were these things called quasars, which they had no idea what they were. But the other school of thought, which essentially won out, was the idea that no. Once the Big Bang occurred, the amount of energy in the universe remains constant. So it's transforming. Stars are being formed, stars are being destroyed, galaxies are being formed, galaxies are being destroyed, the universe is expanding, all these things are happening, but the total energy is constant. Okay, so that's the idea here, is that there's assumptions, right? So the assumption here is that we're not losing any energy in terms of friction. In reality, we would be. And then there would be friction within the bicycle, the structure of the bicycle itself. That's fine. But the point is that the kinetic and potential energy are assumed to be constant the whole time. So the total energy should not be different at F or D. It should be the same. Suppose the bicyclist lets off the brakes and coasts down the valley without pedaling. So that's going from C to D. That's not really a valley there. It's too small. We'll call it a depression. C to D is a valley, okay? Even if there is no friction or air resistance to slow her down, what is the farthest point the bicyclist could reach without pedaling? So here the assumption is no friction, right? So the idea would be you have, potential energy here. And that potential energy is going to be transformed into kinetic energy as you go down. When you reach the minimum, you have the most kinetic energy and the least potential energy. In fact, we'll assume that all the potential energy has been converted into kinetic energy here, okay? So if that's the case, then the highest you could go back up would be the same point, right? Like if you bounce a ball, if you bounce a ball, it will not come up higher than from where you dropped it from. So if you just drop a ball, it's not going to bounce higher. And so, so it looks like the highest you could come up would be about right there. There is no letter at that point, right? I'm just reading horizontally across from C. So it looks like you could get between E and F. So the highest you could get would be E, right? You couldn't get up to F. Okay, now if you pedaled, of course, you could get up to F, but it looks like the highest you could get up is between E and F. So we would just say E. Okay. So that's just, like I said, that's just middle school physics, the idea of transformation of energy, potential, kinetic. And the potential that we're talking about here is gravitational. And in a sense, we consider gravitational energy, potential energy to some extent in here, but not really. Really, we're more interested in electrical potential energy, but the principle is the same. Okay. So let's take a look at, oops. The next problem, and when you look at this, you're gonna see quite a bit of stuff here. This is gonna look like a mouthful. Okay, so take a look at this one. So again, a lot of words. So what you'll see in this chapter is that the problems are word problems generally, and they're pretty lengthy word problems. There's a lot of description going in here. So what you'll want to be doing is really reading carefully what's being written in these questions here. So what I'm going to do is I'm going to draw your attention to the right. Let me see if I can expand this a little bit so you can see it better. That's not too bad, right? That actually looks a little better. There we go. Okay, this is a very interesting and important diagram. It is essentially the basis behind an internal combustion engine, an engine that powers most automobiles, trucks these days, okay? That's going to change. We're going to see more and more electric cars, but even hybrid cars use this principle. So the idea is you have something which is called a gas cylinder. And the gas cylinder is this device right over here, this part of the diagram here. So we have gases in here. Now, in an automobile, what you do is you mix air, which is a mixture of gases, with volatilized or vaporized liquid fuel, right? So you buy gasoline, which is a liquid, but you can smell gasoline, right? That means it volatilizes, it's converted into a gas. So what's done is little volumes of that liquid gas are sprayed out into the cylinder. So the diagram doesn't show that happening, but essentially there's a little entry port where it's sprayed into here as a vapor. And then there's another entry point for air, and air has oxygen gas, 21% oxygen gas. So the fuel is vaporized hydrocarbons, typically with 7 or 8 or 9 carbon atoms and some number of hydrogens, with oxygen gas, O2. And so what we get out of it is a combustion reaction. There's a combustion that occurs in here. And what the combustion reaction will do is it will cause the temperature inside that cylinder to rise very rapidly. And so as a temperature of gases increases, the gases will start to exert a force on this piston. So that's right here. This is called a piston. And the gases will expand inside of the cylinder and push the piston up. And then that piston is mechanically attached to some devices that convert this vertical motion into rotational motion, right? So that's your whole drivetrain of the automobile, and then that will cause the wheels to rotate, right? So the energy is coming from the combustion, which is expanding these gases with enough force to actually push, these pretty strong mechanical devices. And then generally, you won't just have one cylinder, you'll have either 4, 6, 8, or 12. Generally 4 or 6 is most common these days. And so they will take turns, they'll go back and forth. So one will be expanding while the other one is compressing, they go back and forth. and many times every second. And so the device will produce a lot of mechanical energy to propel the device. Okay. So again, this is simplified. They're not showing you, like how the air gets in and how the air gets out, or how the gas gets in or how the gas gets out. But it's, a diagram that kind of shows you the basic principle. And the idea is you've got these gases in here. And when the gases undergo combustion, one of the things that happens is they get hot, right? And it's that increase in temperature that pushes the piston up. But some of that heat is transferred through this metal casing of the cylinder and into the water. And again, a car doesn't have water in here like that. Well, it does have cooling, but in general, there's not like a big bath of water like this. But in any case, if we set it up this way, heat, and we'll talk more about heat, is transferred through the metal and into the water. And notice there's a little thermometer here, right? So this is it's red, which tells us that it's an alcohol that has a dye in it. We used to use mercury, but people are afraid of mercury now. And then you could use some more sophisticated thermometers. I like these ones actually. In any case, so the temperature will rise. So, part of what you're going to be doing is doing some calculations of heat. And in order to do those calculations, we have to know what happens to the temperature of the water. So the temperature change in the water is coming as a result of heat being transferred from the gases into this water bath. And likewise, we could imagine the reverse process occurring. It could be that the gases get cold for some reason. There are ways to make gases cool. And if that happens, then heat will transfer from the water back into the gases. So that can happen as well. Okay. Notice up here it says 1 atm pressure. We're going to talk about pressure. It's related to force and it's related to energy. We'll get to that when we're ready for it. It could be in a minute, could be in a day, we'll see. But 1 atm is what we would consider standard pressure. Okay, so in other words, this is the pressure that we like to use when we're doing experiments. Therefore, we can look up values in tables and all of that kind of stuff. It's also a practical pressure to use because we could just use air pressure, which is essentially 1 atmosphere pressure. So ATM is just an abbreviation for atmospheres. And then we'll talk more about what pressure is. Essentially, pressure is a force pushing down or pulling up over a certain area. And so we'll talk about that as we go further along. Hopefully I won't forget. Okay, so let's come back here. So this is understanding the definitions of heat and work. So we got to talk about heat and work a little bit. Okay. And so let me jump away from this figure and talk a little bit about heat and work. I have a little bit of background to do here. Okay, so heat. We're going to use the symbol Q, a lowercase q. Now, Q is also used for electrical charge, so it can be a little bit confusing. So what we'll try to do is we'll use a lowercase q for heat and then maybe an uppercase q for electrical charge. So heat. So heat is the transfer of thermal energy. So that's a new term. Between one region of space and another region. Of space. So let me show you the simplest situation. Imagine that we have two pieces of metal. Okay, so this is metal 1 and the temperature is 99 degrees Celsius. That's very hot, almost the boiling point of water at atmospheric pressure. Next to that, we have a piece of metal, a different metal, so we'll call it metal 2. And its temperature is 1 degree C. So just above the freezing point of water, right? The freezing point of water at atmospheric pressure is 0 degrees Celsius. So let's write down here that our atmospheric pressure is 1 atm. Okay. So what is observed is that essentially at the atomic level, the molecular level, the hotter a substance is, the faster its atoms move. Okay. So if something is very hot, the atoms are moving very rapidly. If it's a gas, the atoms are free to move around the container. They don't do shapes like that. They do straight lines. Okay, so they're bouncing around. So imagine like if you're playing pool, billiards, hitting the balls, they're all bouncing around there. That's essentially a gas. Okay. At the molecular level, the hotter the gas is, the faster those particles move. The cooler it is, the slower they move. So at some point, if you cool them down enough, they essentially stop moving. Right? Not exactly, but essentially they do. Okay. The hotter they are, the faster they're moving. So what can happen is with this metal, which is at a high temperature, right? 99 degrees C is pretty high. And the other metal at a low temperature, 1 degree C, essentially what happens is the atoms in this substance are moving really fast. Now, it's a solid. Metals are solids for the most part. So how are they moving if they're solid? Well, like springs, like I said, like imagine that the atoms are attached to each other by springs. They vibrate back and forth. And what happens is the hotter they get, the faster they vibrate and the further away the atoms get. The motions become more violent, but also they go faster. So there's a frequency, a speed at which they're vibrating. So the hotter object, these vibrations would be very, very rapid. And the lower object, they would be much, much slower. Doing like that, right? So now here's what happens. Once you put those two metals into what's called thermal contact, meaning temperature contact, those fast things, those fast atoms that are vibrating on the first one will start colliding with the atoms on the other object, the ones where they're moving slower. So they're moving like this. These ones are moving like this, like boom, 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 boom. Well, what happens? If you have something that's moving really, think of a train, right? You get hit by a train, you may not be moving across the tracks. And if the train is, you will be moving after the collision takes place, right? You're going to get pumped right out like that. So the faster these ones are moving on the left and the slower the ones are moving on the right, you have a big transfer of energy occurring. Now they'll scale back, right? Like if things are attached by springs, they'll ricochet back, right? So there's going to be all kinds of collisions back and forth. But overall, statistically, right? Like if you consider all the numbers, eventually you're going to start transferring motion into that colder object. Now, what will happen as that energy is transferred, we call it thermal energy, the motions of the atoms will change. These ones will start to move slower, right? Because they're transferring energy. We can't create energy. So if they transfer some energy to the other metal, they're going to start moving slower. On the other hand, on the right side, they'll start moving faster. Eventually, given enough time, and it could be a second, or it could be an hour, or it could be a year, these atoms in the two metals will be moving approximately at the same speed, the same frequency. Their motions will be the same. Once they are moving at essentially the same speed, now we would say those two metals are in what's called thermal equilibrium. Thermal, like temperature. Now, we can't say how long that'll take. It might be very fast. It might be very slow. Metals conduct heat very fast, so it shouldn't take too long. But eventually they'll be at the same temperature. Now, what temperature will they be at? It kind of depends. It depends on how big the metals are, what their masses are, and it depends which metals we're using. Some metals absorb more heat than others. So we can't really tell without more information, but we actually get to that later in the chapter. But at this point, what we can say is that this metal one, the temperature, so I'll write, I'm sorry, that's not what I wanted to write. The temperature of metal one eventually will be less than 99 degrees C. Okay. Again, we don't know what it'll be. It might be 50, it might be 70, it might be 30, but it's going to go down, right? Over time, as that energy is transferred from metal one to metal two, so this is metal one, that temperature will be less than 99 degrees C. And then the temperature of metal two will be greater than 1 degree C, right? We can't say much more than that, right? Could be 2, could be 3, could be, I don't know, 49 or 50 or 55. We don't know what those temperatures will be, but this one will get hotter and this one will be colder, right? And eventually they will reach thermal equilibrium, okay? So one of the advantages of using water in that water bath diagram is that water absorbs a lot of heat for a low temperature change, right? So if I put a lot of heat into water, it doesn't change its temperature all that much. That makes it very useful for storing energy, right? Put a lot of energy into it, only goes up by 10 degrees C, right? Well, think of the ocean, right? The ocean is an amazing storage of energy, right? Enough that it can produce hurricanes, right? Essentially what happens is sunlight hits the, the surface of the ocean in the tropics. All that intense radiation coming from the sun is right on the surface, goes into vaporizing the water. But like I said, it takes a lot of energy to change the temperature of water. So to actually vaporize it into a gas, that water now has a lot of energy. And that energy then is transformed into something very violent, like a hurricane. Okay. All right. So that's heat. So we now have, a definition. It's the transfer of thermal energy. And in a sense, thermal energy is kinetic energy, right? Because we're talking about these vibrations and we're talking about motion. So that's kinetic energy primarily, right? Between one region of space and another region of space. So this region of space right here, this region of space right there. Okay. We'll come back to the gas cylinder in a little bit. But now let's talk about work. So the symbol for work is W. And when we define work, we're defining it in terms of some sort of concerted motion. So for example, the moving a bus from point A to point B requires energy, right? We would claim that the mechanical movement of the bus is what's called work. So work, W, is the energy used in a concerted, so I'll use the word organized movement of matter. So for example, if I have an object with a mass and I want to bring it up to the top of a mountain, this is mass, not Mars. So I want to move it up to here. That's going to require energy in the form of what we call work. So why is that work and not, let's say, heat? Because it's a concerted motion. It's an organized motion, right? We have this organized matter in the form of a block that we're going to move from one point to another. There are other forms of work. There's electrical work. So like if I want to cause a large number of electrons to move through a circuit in a concerted and organized way, we call that electrical current. That's associated with a form of work as well, electrical work. We don't really talk too much about that in this course. That's, if you take Chem 1200, you'll learn about that a little bit when you do electrochemistry, okay? So for the most part, we're concerned with this sort of work. Now there's a third type of work, right? So there's you know, the movement, the motion of an object, moving an object, right? There's electrical work. The third is actually the one we're going to focus on, which has to do with gases. Okay. So let's come over here to the consideration of what's called compression and expansion. I spelled it. Of gases. It could be one gas, could be a mixture of gases. Air is a mixture of gases. So compression. So what we mean by in this context, what we mean is, let's take our cylinder with the piston. And then we have our gases in here. So this is only a two-dimensional diagram, but it's really a cylinder, right? Like if you take a cup, that's a cylinder. We recognize that's a cylinder, but in, you know, in 2 dimensions, it looks different, right? It kind of looks like a little box in 2 dimensions, but we recognize that's 3-dimensional. Okay. So the idea here is that there's some space inside that cylinder. So there's the volume of the cylinder. We'll call that V. Now, how do you calculate the volume of a cylinder? It's pretty simple. The volume of a cylinder is the area of a circle times the height. So if you've taken calculus, you recognize you can do an integration of circles to get a cylinder. So the area of a circle is pi r squared, where r is the radius, and then h would be the height. So here's our height. That's pretty simple. But remember the radius of a circle. So I'm going to try to draw this a little bit like a circle here at the bottom, right? Because that's a circle. So the radius is half the diameter, right? So the radius is like right there. So there's r. The diameter is 2 times the radius, okay? So the area, I'm sorry, the volume of a cylinder, so all right, cylinder, is equal to the area of the circle, so pi r squared times the height, so times h. And so there's your volume right there, okay? Now, the issue here is it turns out if you have gases inside a cylinder, it requires energy to push them down, to compress. So the first thing that could happen is what we call compression. Okay. And compression is the case where you're squeezing the molecules closer together. It takes energy to squeeze molecules closer together. They don't want to be near each other. At least in gases, they don't. They're colliding with each other, trying to push each other away, right? You know, you realize that, right? Like if you open a balloon, what does the gas do? What does the air in the balloon do? It spreads out. They're trying to move away from each other, okay? So this is called compression. And it takes a certain amount of what we call pressure. We're going to push down on it with what's called a pressure. And we can calculate the mechanical work, W, as being equal to minus, so don't forget this minus, this is important, times the pressure applied. So we're applying this pressure, sometimes referred to as an external pressure. In fact, I'll write external here. External means outside of, so it's an applied pressure. This is equal to, I'm sorry, this is times, I already had the equal sign there. This is times, so I'll put a little X for times, the change in volume of the cylinder, delta V. So delta V is called the change in volume, okay, of the cylinder. So look what happens when you compress a gas or gases. You start with a higher, a larger, a greater volume, after the compression takes place, the gases are closer together. So now the volume is smaller, right? So delta V in the case of compression is negative. So let me write delta V as the final volume minus the initial volume. So you'll see this kind of notation, final, initial, quite a bit. So this would be V final, and this would be V initial.
The change in
I for initial. Yeah, go ahead.
volume is if you're compressing it down, so it'd be like the change in height, in a sense.
Yes, it really comes down to
It's
change
not
in
actually
height.
like change in how much the entire cylinder can hold, because like the cylinder doesn't change the structure itself, but if you're pushing something down in it, it's the change in
That's true.
height of how much, right?
That's right. That's right. So the area, the area is not changing, right? The area of the circle is not changing. It's the height that's changing, right? So sometimes we can simplify this. In fact, we'll see this when we talk more about pressure. We can talk about the pressure being related just directly to the height. Like we can just essentially ignore the area and just worry about the height. So yeah, that's absolutely true. Okay, so you'll see this notation, this delta notation. Delta has different meanings in the sciences. So, one ancient meaning in chemistry is delta means heat. You'll sometimes see this in alchemy. One of the symbols of alchemy is the little triangle, and the triangle means you're adding heat. But in this context, the delta means change in. And actually, if you go on and take more mathematics, calculus, and stuff like that, you'll kind of get that idea. The idea of using D. Delta is the Greek letter D for the idea of change. Okay, so the change in volume. Now that's for compression. And what does this give us? It gives us a way of calculating mechanical work. Now, I didn't derive this. We could go through a whole derivation of this, but I'm not going to do that because it takes a lot of time to go through it and it's not all that useful for us. We're just going to use this equation, right? So we're going to say that if we needed to calculate the amount of mechanical work for compression, we would have negative times the pressure external. So that might be 1 atmosphere, right? Like if it was, just what we have out here in the atmosphere, it'd be 1 atm, or it could be some machine is actually pushing down on it. So it would have a different pressure times the change in volume, where the change in volume is the final volume minus the initial volume. But we can also have expansion, right? So that's compression, but we can also have expansion. So the idea of expansion is we start off with an initial volume. Here's our piston with our gases. And then the gases are going to expand into the cylinder and occupy a larger volume. I made that a little skinnier. There we go, right? You can see this is called expansion. Okay, expansion just means getting bigger, right? And again, the equation doesn't change. Whether it's expansion or compression, we don't change the equation. We don't change the formula. We just change the sign of delta V, because what happens is when you do expansion, the final volume is larger than the initial volume, right? And so if the final volume is larger than the initial volume, then delta V is going to be positive. So I want to write down over here that the case for compression, delta V got smaller. So it's going to be a negative value, right? Because the final volume is smaller than the initial volume. 2 minus 6 is -4, right? But in the case of expansion, we use the same equation, W equals minus P, and now I'll just abbreviate it, EX for external, times delta V of the cylinder. But now for expansion, delta V is positive, right? If you start at 2 liters and you end at 6 liters, 6 minus 2 is +4. So here's a result of this calculation. What ends up happening is for compression, because delta V is negative, right? because delta V is negative, and we also have a negative in front of it, right? That negative is in the formula. It's in the equation. So if we have a negative times a negative, that's going to give us a positive, right? So what will happen here is that delta V is negative, but the work is positive. Okay, I'll put a little circle around for positive. Okay, not electrical charge, right? We're not talking about electrical charges. We're talking about the sign positive or negative of a value. Okay. The opposite is the case over here. Because volume is positive, or the change in volume is positive, then what you have is a positive times a negative. So that gives you a negative. So here, the work is negative. Okay, so negative work is expansion and positive work is compression. The logic behind this is that if you compress a gas, you've given it energy. So the amount of energy it has is greater. So W would be positive. You've done work on the gas. The terminology here can be a little bit confusing. We'll go through it as we look at problems. When you compress a gas, you're doing work on it, and that's positive. When a gas expands, when it undergoes expansion, it's doing work on the surroundings, pushing that piston out of the way, and the sign is negative. That means it's essentially used some of the energy that it had in order to expand the piston. Okay, so that's a lot of background. Let's see if that's enough to be able to do this Alex problems. I can't actually promise that because there's a lot into that problem. It has a lot of kind of nitty gritty. So hopefully we can take a look at this and get to it. So there's a lot of questions here too. So here's our diagram. We went over that. A mixture of gaseous reactants is put into a cylinder where a chemical reaction turns them into gaseous products. So there's a reaction taking place inside here. That's what's happening, okay? The cylinder has a piston that moves in or out. So in means that it's moving down, right? The reason they use in is because if I turn the cylinder upside down, you know, down would be the opposite of what it was if I had it pointing up. So they say in is getting smaller. So in is compression, out is expansion. It moves in or out, meaning down or up, as necessary to keep a constant pressure of 1 atmosphere. Okay, so there's our constant pressure of 1 atmosphere. The cylinder is also submerged in a large insulated bath. See to sketch it right. Okay, so that's all just sort of intro. From previous experiments, so they're telling you that they did an experiment. The chemical reaction is known to release 396 kilojoules of energy. The term there that you want to look at very carefully, you have to read this very precisely. It's like legal language. In this problem, if they use the term energy, they mean total energy, okay? The temperature of the water bath is monitored, and it is determined from this data that 375 kilojoules of heat flows out of the system during the reaction, okay? Now there's a bunch of questions. Is the reaction exo or endothermic? Does the temperature go up or down in the water? Does the piston move in or out? Does the gas mixture do work, or is work done on it? And then finally, how much work is done on by the gas mixture or by the gas mixture, and round your answer to 2 sig figs. Is there, let me just make sure. Okay, looks like that's it. Okay, so let's go through this. There's a little bit more detail I have to give you. Okay, so 1, I'm going to call this delta E is equal to Q plus W, okay? This is called the change in total energy. Now, the technical term for it is really internal energy. Okay. And that is equal to the amount of heat transfer. So we talked about heat and the amount of work done in this process. And be a little ambiguous there, done in the process. So this is really just Q plus W. This is a very important equation. What it says is the total energy of the gases. So this is referring to the gases. The change in energy. So if it takes energy in or puts energy out, that change is equal to the amount of heat that transferred plus the amount of work that was transferred. Just those two together. All you got to do is add them together. Okay. So the main issue here then is just being able to identify in the problem which is delta E, which one is Q, which one is W, right? So delta E, we're going to call that energy. In ALEKS, they just call it energy. Q is heat, and then W is work. Okay. Now, we look at this from the perspective of the gases. Okay. So the idea then would be the following. If it's released to the water is not the gases, then the sign is negative because that means the gases are losing the heat. They're transferring the heat to the water. If it's absorbed by the gases, then the sign of Q is positive. Okay, so in the problem, if it says something like the water transfers heat to the gases, then that's telling you that Q is positive. Okay, they can be worded in many different ways, right? So now what about work? If the work is done on the gases, then it's positive. If it's done by the gases, then it's negative. Okay, that's the terminology that's used here. Now, a little bit of a detail here. If Q is negative, the temperature of the water goes up. And we call this an exothermic process. Exo for out of, okay? So the idea here is the heat is transferred from the gases to the water, so the water will get hotter. Temperature of the water will go up. We're not going to measure the temperature of the gases because it's too hard to measure that. We're just going to measure the temperature of the water. So if it's exothermic, that means heat flowed from the gases into the water, and the sign of Q is negative. If it's the opposite, if Q is positive, then that means the temperature of the water goes down. And we call this an endothermic process. Okay, so endo means going into. So that means the heat is going from the water into the gases. So the gases will get hotter, but the water will get cooler. Okay, just like we talked about a little bit earlier. Okay, so there's a lot, that information, you really want to have that. I would have that all written down when you do these problems, because you have to kind of keep it all straight, right? So there's really only two things we're looking at. We're looking at Q, we're looking at W, and then that allows us to find delta E. But in some of these problems, they'll give you delta E, they'll give you Q and ask for W. Or they'll give you delta E, they'll give you W, and they'll ask you for Q. So you have to keep those three things, straight in your mind, which one is which. And then you have to do the, the language, right? So the in or out, right? In would be compression, out would be expansion, right? And then we have the sign convention. Expansion, W is negative. Compression, W is positive. Okay, so it's all in there. Let's take a look at it again, and then we'll go through it. Okay. So first of all, the first thing they do is they tell you energy. So energy is 396. So they're giving you delta E, right? So if it just says energy, that's delta E. But look how it says it releases. Releases means loses, gives away. So the sign is negative, right? So if it releases, that's negative 396. If it absorbs, that would be positive 396, okay? So delta E for this problem is negative 396. The temperature of the water is monitored is determined from this data that 375 kilojoules of heat, so that's Q, flows out of the system. The system is the gases. So that means Q is negative 375. Flowing out of is negative. And again, you're looking at it from the perspective of gases. So delta E is negative 396. Q is negative 375. Now, endo or exo, that's just heat. Don't worry about delta E. Don't worry about W. Exothermic or endothermic is referring only to the heat. So if the heat is flowing out of, that's exothermic. If it's flowing into, that's endothermic. So 375 heat flows out of the system, out of the gases, right? So careful, not the water. We're not talking about the water. We're talking about the gases. Look at it from the perspective of the gases. So if it's going out of, that's exothermic. So it's releasing into the water 375 kilojoules. So that's exothermic. And does the temperature of the water go up or down? Well, if heat is flowing into the water will get hotter. So the temperature will go up. Does the piston move in or out? In, out, or neither? Now that you have to calculate it. And here's why. We know delta E is negative 396. We know that Q is negative 375, but we don't know W. So we have to calculate W. So let's look at that real quick. Here's your equation, delta E is equal to Q plus W. We want W. How much work? Piston in or out is discussing work. So work would just be delta E minus Q, right? You just subtract Q from both sides. Now, delta E is minus 396 kilojoules. But then we're going to subtract a negative 375. So be careful with your negatives, right? There's a negative here, but Q is already negative. It's negative 375. So when you subtract the negative number, that's like adding a positive number, right? So this is the equivalent of minus 396 plus 375. And then if you have a negative number added to a positive, you just take the difference and whichever one is bigger. If the positive is bigger, then the answer is positive. If the negative is bigger, then it's negative, right? So the difference here would be, what's that, 21. So negative 21 kilojoules. Okay, so there's your work. All right, so now we have answers. We have delta E is negative 396. Q is negative 375. So that's exothermic, right? And now we have W is minus 21 kilojoules. We don't really have a term for that if W is positive or negative, but we could say work is done by the gases on the surroundings. That would be the terminology we use on the piston. Okay, and it's negative. Okay, so that's expansion, right? If it's negative, that's expansion. Sorry, I misspelled expansion. So when work is negative, that's expansion, right? So that means that what's going to happen is the gases are expanding. So the piston is going out or up, if you want to use that terminology, right? It's going out, it's getting bigger, expansion of gases, right? So pretty much that will answer everything, I think. Let's come back over here. It's a lot, right? But once you've done a couple of them, you'll get it pretty good. Okay, so does it do work or is work done on it? Sorry, my battery's getting dead. Work or, okay, so we did that. Oh, sorry. Does the piston move in or out? Because it's expansion, because work is negative, right? What we said was if it expands, that's negative work. That means the piston is moving out. Does the gas mixture do work or is work done on it? That's just the terminology. If the gases push the piston away, they're doing work on the piston. Okay. So does the gas mixture do work or is work done on it? It's doing work. It's pushing the piston away, so it's doing the work. How much work is done on or by the gas mixture? Well, we just got our answer there. Negative 21 kilojoules. Okay, negative 21 kilojoules, right? So there you go. So in a sense, the arithmetic here is ridiculously easy. However, if you don't understand the terminology, you don't really have the terminology down perfectly, there's a very good likelihood you'll get the wrong answer, because you could use the wrong sign for 396, you could use the wrong sign for 375, or you could use the wrong sign for both of them. So there's a lot of errors that can be made, and then you got to know these terms. Okay, so try a few of these. Well, you'll have to try a few of these and go through them. There will be another problem kind of similar when we get into work in the next section. But now what we've covered is an introduction to energy, kinetic and potential. And now we've done a real problem. We've done a real, gas cylinder problem, understanding the definitions of heat and work. So you may need to watch the video a couple times just to really get that down. But luckily we have a weekend coming up. So on Tuesday, when we continue this, we'll start looking a little bit more at, let me just make sure. Oops, sorry. We're going to look at enthalpy. So on Tuesday, we'll work on enthalpy. Okay. All right.
Professor, do you have a couple of minutes?
Yeah, hold on a second.
Yeah.
Sure. So Bianca, you have a question you want to just hang in. Oh, sorry.